In this video, we solved problem 13.5.505 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked the following question. We're told that the radius of a right circular cone is increasing at a rate of 8 inches per minute, and the height is decreasing at a rate of 4 inches per minute. Then the question says, what are the rates of change of the volume and surface area when the radius is 4 inches and the height is 27 inches? And then we're given this, and we're given a box, and we're said, we're instructed to find the rate of change of the volume, some number of inches cubed per minute. And then we want the time rate of change of surface area, which is some number of inches squared per minute. Now, if we don't remember the volume formula or the surface area formula for a right circular cone, and we can look that up. Remember, a right circular cone looks like this. This height meets the circular base at a 90-degree angle, and the height goes straight down to the center of that circular base. And the radius is that distance right there. And all the formulas we need are in the back cover of our book for the Larson textbook. So I've got a right circular cone, and we're told that this is a lateral surface area. So that's the surface area around the outside, which does not include the surface area of the base. So we'll add the surface area of the base as well. Our volume is 1/3 of pi r squared times h. And the surface area is that lateral surface area that was stated in the text, which is pi times r times the square root of r squared plus h squared. That's the area around the outside. So you can think of it like a snow cone wrapper. It's just that area of the paper itself, but not the area of sort of a top to that snow cone wrapper. If we added a top, it would be the area of that circle in the bottom, which is just pi r squared. Okay, so volume and surface area are both functions of r and h. So if we want the time rate of change of volume or the time rate of change of surface area, we've got to use the chain rule. Now, since this is a function of two variables r and h, our dv dt will have two terms. One will be the partial derivative of v with respect to r, and then we'll say, well, let's take that and multiply by dr dt. This term will give us the change in volume with respect to time as that radius changes. Then we'll add this term. This will give us the change in volume with respect to height. Multiply that by dh dt. If we multiply these together, we'll get the change in volume with respect to time as height changes. If we add both of those changes together, we get the change in volume with respect to time in general. Same is true here. Surface area depends on r and h. So I'll have the partial derivative of s with respect to r and the partial derivative of s with respect to h there. And both of those are multiplied by the respective derivatives with respect to time. So I can think of this as the change in surface area with respect to time as the radius changes, plus the change in surface area with respect to time as the height changes. Add those together and you get the change in surface area with respect to time in general. Now, a problem statement gives us a lot of this information. So we should go back to the problem statement and make sure that we can infer what's given. So let's state that given information here. First, we're told that the radius of a right circular cone, is increasing at a rate of 8 inches per minute. As soon as I see inches per minute, and I know I'm talking about the radius, that tells me the derivative of the radius or derivative of r with respect to time is equal to 8 inches per minute. And I know that that's the derivative of r with respect to time because the units of the numerator are the units for the radius, and then we're dividing by minutes, which are units of time. Similarly, we see that the height is decreasing. So that means the rate of change is negative at a rate of 4 inches per minute. So that means dh dt is negative 4 inches per minute. So I will have 8 inches per minute here, and negative 4 inches per minute here and here. And then we'll just need to compute a couple of partial derivatives. This partial derivative of V with respect to R and with respect to H, and similarly the partial derivative of the surface area with respect to R and H. Let's do part A first. The partial derivative of V with respect to R, which can be denoted that way if you prefer, is the partial derivative with respect to R of this function. Now remember, when you're taking a partial derivative, you think of the other variables as constants. So this is just a constant times R squared. I would factor out that constant, write it down, and then multiply by the derivative of R squared. So I'll take the derivative of R squared, which will give me a 2R. 2 times the 1/3 will give me a 2/3. So I've got 2/3 pi times R times H there. Now, let's read further. It says, what are the rates of change of the volume and surface area when the radius is 9 inches? So I don't just want it in general. I want those when R is equal to 9 and when the height is 27 inches. So this is a particular instant in time when R is equal to 9 and when H is equal to 27. So that is our change in volume with respect to the radius in general, but at the point of interest, that's when RH equals 9/27, we would have 2/3 times pi times 9 times 27. And of course, 3 goes into 9 3 times, and 3 times 27 is 81. So we end up with 81 times 2, which is 162 times pi. And the units are the units of volume, which are inches cubed, divided by the units for the radius. Now, don't simplify that to inches squared. You want to think of this as a 162 pi inches cubed change in volume for every 1 inch increase in the radius. So we know that that's true. And then we also need the partial derivative of V with respect to H at the point of interest. You could use subscript notation if you wanted to. But we've got 1/3 pi R squared times H. And again, you're thinking of the R as a constant. So I've got a constant times H here. The derivative of a constant times my variable is just that constant. And then I will evaluate that at the point of interest. So the partial derivative of V with respect to H at R equals 9, H equals 27 is this. We get 1/3 times pi times 9 squared, which is 81. 81 divided by 3 is 27. So we get 27 pi inches cubed per inch. So this is saying as the height increases by 1 inch, the volume increases by 27 pi inches cubed. And you can imagine that as it gets 1 inch taller, the volume increases by that much. Or for this one, that 162 pi inches cubed, as the radius increases by 1 inch, the volume would increase by that much at the particular instant when R is already equal to 9 and H is already equal to 27. So I've got this piece, and I've got these two derivatives, so I can just substitute those in. The change in volume with respect to time is this, of course, evaluated at R naught, H naught, the point of interest, times dr dt. This gives me the change in volume with respect to time as the radius changes. Then we add this derivative at R naught, H naught, times dH dt, which gives us the change in volume with respect to time as the height changes. This first piece was 162 pi inches cubed per inch. And the second piece, and then we're multiplying by dr dt, which was given to be 8 inches per minute. So we're told the radius is increasing at 8 inches per minute, and the volume is increasing at this many inches cubed per inch. And so when you multiply those together, you get the number of inches cubed change in volume per minute as the radius changes. And then we'll add this piece, which was 27 pi inches cubed per 1 inch. And then we'll multiply by dH dt, and dH dt is -4 inches per minute, because every minute looks like that height is dropping by 4 inches. We multiply those together, we get the amount the volume should decrease as that height drops by 4 inches per minute. And it'll give us the number of inches cubed per minute that the volume should drop. Now, when we add this to this, then we get the total change in volume with respect to time. So we'll have 162 pi inches cubed per minute minus 4 times 27 pi inches cubed per minute, which gives us 54 pi inches cubed per minute. That's the change in volume with respect to time for that right circular cone under these circumstances at the particular instant when R is equal to 9 and H is equal to 27. Actually, I just realized it should be 162 times 8. Sorry about that. Forgot to multiply by 8. 162 times 8 times pi minus 27 times 4. And let me correct that number. That should be 1,188 pi inches cubed per minute. There we go. That's better. Okay, we're going to do the same thing with the rate of change of surface area, and this is our surface area function. So surface area is a function of R and H. So we need the partial derivative of S with respect to R and the partial derivative of S with respect to H, so that we can substitute those in here and use the dr dt and dH dt as well. We'll substitute everything that we need to substitute and then simplify to get the change in surface area with respect to time. Now for this, it's helpful to write that square root in the following way. Remember, if you have the nth derivative of x to the m, that's x to the m over n, the index of that radical goes in the denominator. Now with a square root, there's an implied 2 there. And if there's no exponent, and there is no exponent here, don't be tempted to think it's a 2. This is a sum that we have to evaluate first. That whole expression is being raised to an implied first power. We would think of this r squared plus h squared as being raised to the 1/2 power, just applying that rule. When we write it like that, it makes it a little bit easier to compute the partial derivatives. So let's take the partial derivative of S with respect to R first. You can write it that way if you prefer. Now for this piece, I've got pi r times that square root, or times that expression to the 1/2 power. Since this is a function of R and this is a function of R, I want to use the product rule. We'll have derivative of the first with respect to R, treating H as a constant, times the second undifferentiated. So you just write it down. Don't do anything to it. And you'll add the derivative of the second. And for right now, I'm just going to write that down. We'll compute that in a moment. Times the first undifferentiated, which in our case is pi r. That's the derivative of that piece. And then we have to add the derivative of that piece. Pi is just a constant. We multiply by the derivative of r squared. So you bring the power down, multiply by r to the 1 less power. Okay, so we're here. Now we just need to compute these two derivatives. Pi is just a constant. So this is the derivative of a constant times r with respect to r. The derivative of a constant times r is just the constant. So we'll have pi there. And I will put this back under the square root. And then over here, we've got to use the chain rule. Notice we've got a function nested inside that function to the 1/2 power. We've got that u to the 1/2 is our outside function. And that's our inside function. So use the chain rule. Now remember, the chain rule says that you take the derivative of the outside first. So the derivative of a function to the 1/2 is a 1/2 times that function to the 1/2 minus 1, which is -1/2. You want to put your inside function back inside. and then multiply by the derivative of the inside, just a partial derivative with respect to r, by the chain rule. That is the derivative in red. Don't forget to multiply that by the pi r. And then this piece turns out to be 2r for that. And that doesn't have any r's in it. So, and h is being treated as a constant. The derivative of a constant with respect to r is just 0. So we just get this is 2r. Now this 2 times that 1/2 is going to give us a 1. I have 2 halves, I have 1, right? And we can simplify further if we want to. That expression to the negative 1/2 is the same as that expression to the positive 1/2 in the denominator. And the positive 1/2 power is just the positive square root using this property right here. In the numerator, we have a pi times an r times an extra r, that's pi r squared. And then we've got this extra term over here. Now we could do the work to simplify further if we wanted to, but you don't have to. Some students might like to get a common denominator. So they might multiply by the square root of r squared plus h squared over itself so that these have a common denominator. You don't have to, but you can if you want to. So that'll give us pi times r squared plus h squared plus pi times r squared all over the square root of r squared plus h squared plus this 2r. You could keep going and get a common denominator over here as well, but I wouldn't. This is a pi r squared plus another pi r squared. That's 2 times pi r squared plus pi h squared all over that square root. Again, this is not necessary, but you can compute it if you want to. All right, now we want dSdt when r is equal to 9, when h is equal to 27, and when the rates of change of r and h are these with respect to time. So that means we need to compute this and this, those two partial derivatives at these particular values of r and h. So I will evaluate my partial derivative of s with respect to r, this time using subscript notation, at r equals 9 and h equals 27. So this is 2 pi times 9 squared plus pi times 27 squared all over the square root of 9 squared times 27 squared plus 2 times pi times r, which is 9. So that is 81 times 2, or 162 times pi, plus, well, I don't know what 27 squared is off the top of my head. Look, turns out to be 729. And that's multiplied by pi as well. And then we'll divide by the square root of 9 squared plus 27 squared. That's 810 plus 18 pi. Of course, 810 factors to 81 times 10. And then in my numerator, I've got 162 times 729 times pi. Excuse me, 162 plus 729, which is 891 times pi. In the denominator, that was the square root of 810, which we said was square root of 89 or 81, which is 9, times the square root of 10. Okay, so that's that. If you want, you can get a common denominator, but it's not necessary. Okay, now we also need to find the partial derivative of s with respect to h, or in Leibniz notation, we could write it that way. It's the partial derivative with respect to h of this expression, pi r times r squared plus h squared to the 1/2 plus pi r squared. Now this time, h is being treated as our variable and r is being treated as a constant. So this is a constant times a function of h, excuse me. So we don't need the product rule here because we don't have a function of h times a function of h. So bring the constant down first. Just like if there was a 3 out front, you'd bring your 3 down. And then for this piece, I see a function nested inside of that 1/2 power function. So we're going to use the chain rule again. According to the chain rule, you take the derivative of the outside first. So you bring the 1/2 down, and you multiply by the inside function to the negative 1/2. So 1/2 times the function to the 1/2 minus 1, which is negative 1/2. Then you put the inside function back inside, and then you multiply by the derivative of the inside. So this is the derivative of the outside evaluated at the inside without changing it, times the derivative of the inside. And now that's a partial derivative with respect to h, treating r as a constant. And this doesn't have any h's in it, so we'll get a 0 there. Now for this piece, r squared doesn't have any h's in it. That's just a constant. The derivative of a constant with respect to h is just 0. Then we'll add the derivative of h squared with respect to h, excuse me. That's just 2h. You bring the power down, multiply by h to the 1 less power. Of course, we don't write h to the first, we just write h. Now, the 2 times the 1/2 just gives us a 1. So we end up with this. Pi times r times h, that goes in the numerator. And then we're dividing by the square root of r squared plus h squared, because that's what that expression to the negative 1/2 is. We can put it in the denominator that would make it positive 1/2, and anything to the 1/2 power is the square root of that expression. And then we're adding 0, so it doesn't do much after that. Now we want that evaluated at r equals 9, h equals 27. So we'll have pi times 9 times 27 all over the square root of 9 squared plus 27 squared. Now 9 squared plus 27 squared should be that same 810 from before. Yep. And the square root of 810 is square root of 81, which is 9 times 10. And of course, those 9s reduce. And so you end up with 27 times pi over the square root of 10. Now, I didn't mention the units for the last one, but we ought to. This is a partial derivative of s with respect to h. Actually, it's the same units for this one. So we'll have the units for the numerator divided by the units for the denominator. So this is some number of inches cubed per 1 inch change in height. Now this is similar, excuse me. Excuse me. This is the partial derivative of s with respect to r evaluated at 927. So of the units of the numerator over the units of the denominator here, those are also inches cubed, excuse me, inches squared per inch. I said the wrong thing there. It should be inches squared per inch. Don't simplify to inches. It doesn't really make sense. This is the number of inches squared. Our surface area will increase for every 1 inch change in the radius. And this is similar. This is the number of inches squared. Our surface area will increase for every 1 inch change in the height this time rather than the radius, because this is the partial derivative with respect to the height. And of course, at the same time, we're treating the other variable as constant. So we've got those two partial derivatives. And we want to find the partial, or excuse me, just the ordinary derivative of s with respect to time. So it'll just be this product. And this first expression, evaluated at the point of interest, is 891 pi over 9 root 10 plus 18, or 18 pi, that's some number of inches squared per inch. And we're going to multiply by the rate of change of the radius with respect to time, which we were told at the very beginning was 8 inches per minute. When we multiply those together, we get the change in surface area per minute as the radius changes. Then we're going to add this partial derivative, which is given by that. It's also number of inches squared per inch. We're going to take it and multiply by dH dt, which is -4 inches per minute. These reduce. And so that decrease in the height per unit time is going to cause the surface area to drop, and it's going to drop by this much as the height changes. So if you multiply all of those together, you get 891 pi over 9 root 10. I think I might multiply this one by 9 root 10 as well. So I have 9 times 18 times pi root 10 over 9 root 10, all multiplied by 8 plus 27 pi times -4 over square root of 10. And this will all be in inches squared per minute when we're done. So we end up with, let's see, 891 plus 9 times 18 times the square root of 10. That is the numerator here. We want to take that and multiply by 8. And we want to divide by this product, 9 times the square root of 10. That's this expression here. And then we want to subtract 27 times 4 times pi. Actually, I'm not sure I even included my pi, so let me do that again. Got 891 plus 9 times 18 times the square root of 10 divided by 9 times root 10. And I did not multiply by pi this time. That gets multiplied by pi. That's this number here. Then we want to multiply by our 8 inches per minute. So we get that number. And then we want to subtract from that this 27 times 4 times pi divided by the square root of 10. And maybe we want an extra set of parentheses there. And I get approximately 1,131.915 inches squared per minute. Now, they might not be happy with this. If they want an exact value, we've got to do a little bit more algebra there. In that case, and I think they do want an exact value, I should divide this by 9. 891 turns out to be 99 times 9. So I've got 99 times 9 pi there, plus, should be adding that, plus 9 times 18 pi times root 10 over 9 root 10. And with that in mind, I can reduce those 9s. And then we see what we've got. We have 99 plus, from here, 18 root 10. Factor out that pi, all divided by the square root of 10. If you want, you could factor out a 9 as well. We've got 9 pi times 11 plus 2 root 10, all divided by root 10. So that's an alternate form of that expression. We want to take that and multiply by 8. So it's going to give us 72 pi times 11 plus 2 root 10 over root 10. Now over here, we've got -27 times 4, or 4 times -4 times 27, which is -108 times pi over root 10. Now, if you want, you could distribute that 72 2 to the 11 here and subtract that 108 pi over root 10, because you'll have 72 times 11 pi. 72 times 11 is 792, and then we'll subtract 108 from that. So we'll end up with 684 pi, just from this times this minus that. And then the other term would be 144 pi root 10 all over root 10. Now we're just doing arithmetic here, but if someone wants you to rationalize that denominator, you could multiply by root 10 over root 10. Then you'd have 684 times pi times root 10 plus 144 times 10. So that's 1,440 times pi over root 10 times root 10, which is 10. And now I've got an even number here and an even number there, so I could divide everything by 2 if I wanted to. This is just a lot of arithmetic at this point. So I have a 2 times 342 pi root 10 plus 720 pi, all divided by 10, which is 5 times 2, so the 2's reduce. And you might say to yourself, well, what do 720 and 342 have in common? Now, it's not at all obvious, but they do have a factor of 18 in common. You might have reason to believe that they have a factor of 9 in common. So I would do 342 divided by 9. That's 9 times 38 pi root 10 plus 9 times 80 pi would give me that second term. And then I would see that the 38 and 80 still have another factor of 2 in common. So I could factor that out. The 2 times the 9 would give me an 18. And then I would be left with, well, half of that 38 there, which is 19 times the pi times the root 10. And if I've divided that by 2, I get 40. Now 19 and 40 don't have anything in common, but these two terms do have the pi in common. So you could factor that out. So I would write it like that. We get 18 pi over 5 times 19 root 10 plus 40. And I believe that is what WebAssign wants. Now, again, we were just doing a lot of arithmetic for a long time to get the exact answer. This is the approximation, but for the exact answer, we needed to keep everything in terms of those radicals and simplify all those powers of 9 or factors involving 9 as much as possible. But ultimately, this was a change in surface area with respect to time, and our inches, or our units, excuse me, would be the inches of the, or the units of the numerator, excuse me, by the divided by the units of the denominator. I'm sorry, it's getting late. It's about midnight here. It's inches squared per minute. And that would be our final answer.